Hi, I'm Samuel Rue, founder of Gateway Corporate and host of this web series on signal processing. I hope you enjoyed the video. In this presentation, I'm going to walk through the Viterbi algorithm. This is a core algorithm in signal processing, probabilistic modeling, and sequence decoding. The big idea is simple. When data is noisy, incomplete, or partially corrupted, Viterbi helps us reconstruct the most likely original signal. In many real-world systems, what we observe is not the true underlying signal. Instead, we see a noisy version of it or one with missing values. The actual symbols or states we care about are hidden, and our goal is to recover the most likely hidden sequence that produced what we observed. To model that, we use a Hidden Markov Model, or HMM. To use an HMM, we need a few ingredients. First, a set of possible hidden states. Second, an observation sequence, which is the data we actually receive. Third, start probabilities, which tell us how likely each state is at the beginning. Fourth, transition probabilities, which describe how likely it is to move from one state to another. And finally, emission probabilities, which tell us how likely a state is to generate a particular observation. At first, you might think we could just test every possible hidden sequence and pick the best one, but that becomes infeasible almost immediately. If there are n possible states and t time steps, then the number of possible paths is n to the t. That grows exponentially, and even for modest values of n and t, brute force becomes far too expensive. The key insight is from dynamic programming that we don't need to recompute everything from scratch. If we want the best path ending in some state j at some time t, we only need the best paths to each state at time t-1, plus one transition step and one emission step. This means that we can build the solution incrementally, which is what makes the Viterbi algorithm a dynamic programming algorithm. So our core recurrence, because this is a recursive algorithm, for each time step t and each state j, we compute the best score of any path ending at that state. We do that by taking the maximum over all previous states I, adding the previous best score, the transition probability from I to j, and the emission probability of observing the current symbol from state j. In practice, we usually work in log space, which turns products into sums and improves numerical stability. At time 0, there is no previous state, so initialization is simpler. For each possible starting state, we take the log of the start probability and add the log of the emission probability for the first observation. That gives us the initial score for each state. And since there is no predecessor yet, the back pointer is null. Back pointers. This is the most important implementation detail. When we choose the best previous state for each cell, we also store which predecessor gave that best score. That stored predecessor is called a back pointer. After we fill the entire dynamic programming table, we do not know just the best final score. We can also trace backward through the back pointers to reconstruct the full most likely path. In code, the algorithm breaks into 3 clean phases. Initialization sets up the first column of the dynamic programming table. Scoring fills in the rest of the table using the recurrence. And traceback reconstructs the best path by following the back pointers from the final state back to the beginning. Here, the observed text is first normalized into a clean sequence of symbols. If the sequence is empty, the function returns immediately. Then the score table and back pointer are allocated. For the first time step, each state gets its initial score from the start probability plus the emission probability of the first observation. Each back pointer is set to null because there's no previous state yet. This is the main dynamic programming loop. For every time step after the first and for every current state, the algorithm checks all possible previous states. It computes a candidate score for each one using the previous score plus the transition cost. It keeps the best of those candidates, stores the best score, and then adds the emission score for the current observation. At the same time, it records which previous state achieved the maximum. After the table is filled, it also selects the best final state by scanning the last column. Once the final state is known, traceback begins. The algorithm creates an array for the final path, places the best final state at the end, and then walks backward through the back pointer table. At each step, it follows the stored predecessor and fills in the previous position and the path. When that process reaches the beginning, the full decoded sequence has been reconstructed. So at this point, we can switch over to the live demo, where I'll show you that we have the code loaded up here. We have the function Viterbi decode. Here is the initialization step. Here is the scoring step. And then finally, here is the back propagation step. And I can load up our notebook in Node.js. And we have this original string, Hidden Markov Models can predict noisy text. And we corrupt it with some noise. So you can see here the question marks represent unknown characters, and some of the characters are indeed swapped. And we have our decoded version here using only the Viterbi algorithm. And finally, we have a dictionary matching algorithm so that once we decode with Viterbi, we can match it to the closest dictionary words. And indeed, we see Hidden Markov Models can predict Daisy Lest, which is not exactly Hidden Markov Models can predict noisy text, but close enough. And if you look, you will see that the accuracy ranges from about 70 to 80%. In conclusion, Viterbi is dynamic programming over states and time. Recurrence computes the best score per cell, and backpointers reconstruct the full path so that we can determine the most likely hidden state from our observed state. Some links here. You can subscribe on YouTube at youtube.com/@ApolloVision. I appreciate all likes and subscriptions. They go towards improving the channel and making sure that we get noticed by the algorithm. You can follow me on X at x.com/Samuel_Rue_. You can email me at office@gatewaycorporate.org. And you can reach me on IRC at irc.technet.chat at the Information Superhighway channel. Thank you very much for watching. I really appreciate it. Please leave a like and subscribe if you enjoyed the video.